Hi everyone, we're going to look at solving exponential equations as well as solving logarithmic equations. So we're looking at 2e. The first page of this packet, so like the front here, is what we did as an exploration. So we're not going to go through every little piece, but the main thing is this statement down here. So the takeaway from this exploration was that a logarithm is the inverse to an exponential equation. And if a log is an inverse to an exponential, that means an exponential is also an inverse to a log. So I'm going to add that at the bottom here. And that's the only thing from the front that we're going to talk about in the video, and then we'll go through some examples together. So when I flip the page over, we're going to first look at solving exponential equations. So we have some steps that we want to follow, and we're going to go through a couple together, but we're not going to do all of them. So an exponential equation is when our variable is in the exponent. So we can see that in the examples up here. And then our first thing that we want to do when we solve this is isolate the exponential expression. What I mean by that is wherever your variable is, it's connected to a base that has that exponent. That needs to be by itself. So if I look at this first example here, my variable is this x in the exponent on the 2. I don't want anything with that 2 to the x. So this one is actually already isolated because nothing's near it. If I look at this one, my variable is here in the exponent on the 20, so I don't want anything with this 20. And so this 6, because it's being added, I would have to move first because right now it's not isolated because of that 6. So that's what I mean by isolating it. So then for step 2, we want to take the log or natural log of each side of the equation. And the reason we're doing that is because we know that a log is the inverse of an exponential, and if our variable is in the exponent, it's an exponential, and so we want to undo that and then use our laws of logarithms to bring down our exponent, and then we can go ahead and solve. One thing I want you to note here, if we have e with the exponent with a variable on e, we have to use natural log. And that is because natural log has an understood base e. So if we see e, the natural log will cancel that out. A regular log will not. Anything else, we can use either or. So we can use log for almost anything. We just can't use it for e, but we can use natural log for anything. So I'm going to go through a couple examples. I'm going to start with a. So I notice that my variable here is in my exponent on the 3. That needs to be isolated. And right now it is, because the plus 2 is a part of that exponent. So nothing is being added or subtracted or multiplied to the 3. So step 1 is done. So then I want to move on to step 2, and I want to take the log of both sides. So I'm going to do log of the left side, which is 3 with an exponent of x plus 2. And then I also am going to do log of the right side, which is 7, so it'd be log of 7. When I do my log rules, I know that I can pull this exponent down in front as a coefficient. So when I rewrite this, I have x plus 2. And I'm going to put that inside parentheses because it was in the exponent together. and it's being multiplied to log of 3, and then nothing changed on the right. So I'm just going to rewrite that. So if I want to solve for x, I need to get rid of this log of 3. So I'm going to divide by log of 3 on both sides, because whatever I do to one side, I have to do to the other. Log of 3 and log of 3 will cancel each other out. So I am left with x plus 2 equals log of 7 divided by log of 3. Well, this right here, since our base is an understood 10, I can type that in my calculator. So I'm going to do that right now. I hope you can see this. So my log button is next to the number 7. So I have log of 7, and I'm going to close my parentheses, and I'm going to divide that by log of 3. So log of 7 divided by log of 3, and I have this lovely decimal. So I'm going to have 1.771. And then to finish solving this equation, I'm just going to subtract 2 on both sides. So minus 2, minus 2. I get x all by itself. So I'm actually going to just take this number and do minus 2. So I'm taking my previous answer. I think you can see that. We'll do that. Subtract 2 from it, and I end up with negative 0.229 if I round it. So that is going to be my final answer for my variable. Oh, I realize that pen is not working so well. So I want to do B, because it's a little bit trickier than the one we just did. So looking at our equation in B, I want to first find where my variable is. So my variable is in the exponent on E, so I have to make sure E is all by itself and isolated. Right now, the 8 is being multiplied to it, so I have to get rid of the 8 first. So to start, I'm going to divide both sides by 8 so that my 8's cancel and I can get my exponential term isolated. So I'm left with e to the 2x equals, and then 20 divided by 8 ends up being a decimal, but since it's not repeated, I'm going to write it as a decimal, so 2.5. Now I did step 1. If I want to solve exponential, I have to take log or natural log of both sides. If I have e, I have to use natural log. So I'm going to rewrite this as the natural log of the left side and the natural log of the right side. And then if we need to write a note, so we can remember if we look back at our notes later on, we're going to take ln of both sides. When I do that, I can do my laws of logs and pull my exponent out in front. So I have 2x times natural log of e equals natural log of 2.5. There's a couple ways I can go about this now. I can divide both sides by the natural log of e, figure out what the number is on the right, and then divide by that 2 to solve for x. But I actually want to pause for a second, because if natural log has a normal understood base e, and it's natural log base e of e, that is actually something special. So in our calculator, I'm going to put it on this side. I'm going to do natural log of e, and e is on your calculator twice. So there's one above the natural log button, and there's also one above your division button. So I'm going to use this one because my invisible exponent is 1. So I'm going to do natural log of e. And when I hit enter, I get 1. So that means that this piece right here turns to 1. So I technically have 2x times 1 equals natural log of 2.5. Well, 2x times 1 is still just 2x. So you don't have to write that middle step there, but I'm going to for the sake of the video. And then to solve for x, I just want to divide both sides by 2. So I'm going to divide by 2, divide by 2. So I'm going to do the natural log of 2.5 in my calculator and divide that by 2. And I get 0.458 since I want 3 decimal places. And that is my final answer. I'm not going to do both C and D, but I do want to kind of briefly talk about them to get you started. So looking at C, I have variables on both sides, both as exponents. So this one is on the 6, and this one is also on the 6. And right now, each side of my equation is already isolated. So I do want to start by taking the log or the natural log of both sides. And it doesn't matter which one I do, you'll get the same answer either way. So if I want to do, well, I'll do log still. If I do log of the left side of my equation and then log of the right side of my equation, I know that I can pull down my exponents. So my negative r on the left will pull in front of log, and then my 3r minus 1 will pull in front of the other log. So what I will end up with is negative r times log of 6, and then 3r minus 1 times log of 6. Since they're being multiplied, I can go ahead and divide both sides by log of 6. And that's really nice because they will cancel on both sides of my equation. So these cancel and these cancel, and I'm left with negative r equals 3r minus 1, and I can solve that. I realize I'm actually pretty close. I might as well just finish this problem. So this is what we're left with. If I want to solve for r, I'm going to subtract 3r from both sides. So I'm left with negative 4r equals 1. I divide both sides by negative 4. I get r equals negative 1/4. Or we could write it as a decimal, negative 0.25. Either or will work. For D, my variable is in the exponent on this 4, and so I have to get this isolated, which means I have to get rid of 64. So I would start by dividing both sides by 64, and then I can move on to taking the log or natural log of both sides. But I'll leave that one for you to do. So at the bottom, we have a word problem that is related to exponentials and solving them, and it talks about a secret, and you tell someone every day, and that person tells someone every day, so on and so forth. So we're trying to figure out on what day will 64 people have heard the rumor, and then on what day will the whole city of Kentwood with this population have heard the rumor. So to start, I just kind of want to get an idea of on day 1 how many people have heard the rumor. Well, on the first day, I told my best friend, so that's a total of 2 people, me and my best friend. On day 2, we each told someone else, and so that would be a total of 4 people because there were 2 people, they each told someone else, so that's 2 more, which is 4. On day 3, if 4 people knew and they each tell one other one, it doubles again, so that would be 8. And I could keep this pattern up until I get to 64 to figure out what day that would be. That would work for part 1. For the second part, though, I'm not going to keep this table going until I get to 54,000, so we have to figure out something else. So, since this is doubling each time, the equation that represents this would be y equals 2 to the x, where x is our number of days and y is our people. So if I want to figure out when 64 people have heard it, I'm going to plug 64 in for my y, and then I have to solve for x. I don't have much room, but to solve this, I'm going to use the same method as we did in the top ones that we did. So I'm going to take the log of both sides. So I have log of 64 equals log of 2 to the x. I can pull my exponent down as a coefficient. So I have log of 64 equals x times log of 2. And if I want to solve for x, I'm going to divide both sides by log of 2. So I have log of 64 divided by log of 2 equals x, and I can figure out what day that is. So in my calculator, log of 64 divided by log of 2, and I get on day 6. So now that we can solve it without the table, I can solve part 2. I know my population is 54,141, and I want that to represent the number of people, so that's going to replace my y, and I can go ahead and solve this. I can do all the middle steps, so I take the log of both sides, I bring down my exponent, and I'll end up with log of 54,141 divided by log of 2 equals x. So let's figure out what that is. I got 15.724. So 15.7. Now, since we're given a context here, we're talking about the number of days. We don't know at what time of the day the rumor is spreading. So we can't say 15.7 days because that doesn't make sense. And so we have to round up to 16 days, or on day 16. That many people will have heard it. It cannot be 15 days because if we went down, we would not have enough people who know the rumor that would be the population of Kentwood. So we have to round up to 16 days. All right, so this page was solving exponential using logs, and now we're going to flip, and the other part of 2e is to solve logs using exponentials. So a logarithmic equation is when we have a variable that occurs within a logarithm, so a log or a natural log, and the guidelines for it are listed out for us. The first step is the same. We want to isolate the log expression in our equation. So for a, natural log of x plus 2 is already isolated on the left side of our equation. So step 1 is done. So then for step 2, we have to raise the base number to each side of the equation and then cancel out the logarithms. That probably sounds weird without seeing what that looks like, but I do want to put a couple notes here before we do it. If we have natural log, we need to know what the invisible base is. So natural log has a base e, which we briefly talked about. The other one is if we have log and it doesn't specify, it has a base 10. Now if we have a log and we see the base, well, obviously it's just 3. The base is 3. If we look at C here down at the bottom, we see the base is 9. So if we see a base, that's different. If we don't see a base, we need to remember these two things. So back to A, I have my log already isolated. My base on this natural log is a base e. What that means is I'm going to use e as a base on each side of my equation, and I am going to write all of this as an exponent on e. So I have natural log of x plus 2 all as an exponent. And then on the right side, same thing. Whatever I do to the left, I have to do on the right. So this 5 becomes an exponent on e. So both sides became exponents on e. And the reason it's e is because that's the base on my natural log. So now if I have e raised to the power of natural log of e, those are inverses of each other. We can cancel those out. So that's why we did this, so we can get rid of our natural log. What I'm left with is this x plus 2. So my log is gone, so it's no longer in the exponent. So I have x plus 2 equals e to the 5th. If I want to solve for x, I subtract 2 on both sides. I get x equals e to the 5th minus 2. And it does say it around to 3 decimal places. So in my calculator, I'm going to figure out what that is. So my e button, I hope you can see it, is down here. On mine it's in yellow, so I'm going to hit my yellow second button first. So I'm going to hit second, natural log. So I have e to the 5th, close my parentheses, minus 2. So my x is equal to 146.413. And we were able to solve our natural log. So let's look at b. Gets a little bit more complicated, so I want to find my variable. My variable is here inside this log, so I first want to make sure it's isolated. It's not. I have this negative 10 out here, so I have to move that first. So I'm going to add 10 onto both sides so I can isolate my log. I'm left with log base 3 of n plus 3 equals negative 10 plus 10 is 0. Now I have to get rid of my log. Well, the inverse of log is exponential. So I look at what the base is on my log, which is 3. And that's going to become the base for my exponent. So 3, and then I'm going to raise everything as an exponent on the left. Same thing on the right. I have 3. I raise as an exponent, so the 0 becomes an exponent on that 3. So I want to figure out what cancels out. So I know my 3, log of 3 will go away. Cross those out. Do not cross out your n plus 3, that stays there. And then using our exponent rules, we know that anything with the power of 0 turns to 1. So all of that turns to 1. And this looks much easier to solve, so I can solve this for n, and I get n equals negative 2. And that's my final answer. We're going to do one more. So I'm going to scoot this up. And we're going to do C because C is more complicated than D. We do actually end up starting these the same way because when I first look at this, I notice I have 3 logs. I have 2 logs just on the left side of my equal sign. So I want to start by condensing these using our log rules. So since I have addition on the outside of my logs, I can combine it into multiplication on the inside. So I'm going to have log base 9 of x plus 6 times x, because I do x plus 6 times x, and that's going to equal log base 9 of 27. And I'm just going to leave that for now. I just condensed these into a singular log. So now if I want to get rid of my log, I have to do the inverse of logs, which is exponentials. So I'm going to raise everything to an exponent on 9. And the reason I know it's going to be 9 is because that's the base on both of my logs. So I have 9 raised to the power of log base 9 of x plus 6 times x equals 9 raised to the power of log base 9 of 27. I can cancel out my 9 log base 9 on both sides. So what I'm left with is x plus 6 times x equals 27. I'm going to multiply these out, so I actually have to distribute the x into the x and the 6. So I'm going to have x squared plus 6x equals 27. And what I have right here is a quadratic. So I have an exponent of 2 as my biggest. If this is a quadratic, I have to get it equal to 0 so I can solve it. So I'm going to make a note here. So to solve a quadratic, we have to get it equal to 0. So I'm going to subtract 27 on both sides. So I have x squared plus 6x minus 27 equals 0. Let's scoot this up a little bit more. To solve a quadratic, we can either factor it or use the quadratic formula. I'm going to factor it because I think I already know what pair of numbers it'll be. I'm going to have x plus 9 and x minus 3. Positive 9 times negative 3 will give me a negative 27. If I add 9 plus a negative 3, it will give me a positive 6. So that's where I got those two numbers from. To solve this, I break this apart into a mini equation and set it equal to 0. Same thing with the other one. And I get two answers. I get x equals negative 9 and x equals 3. We do have to double check a couple things because if we look back up here, I want to look at this one. So if I have log base 9 of x, we're going to test out some things in our calculator. So I know this is technically base 9 and we're going to do base 10 in our calculator, but I want to prove something. If I do log of 3, so of the positive 3, and I hit enter, I get a decimal, and I would be able to round that. Now if I do log of negative 9 and hit enter, I get non-real answer. So you can see I did type in the negative 9. What that means is we cannot take the log of a negative number. It is undefined. And so because we would actually plug in a negative number here, negative 9 cannot be an answer. Negative 9 here, well, if we did negative 9 plus 6, that would be negative 3. That would still be negative. So we're going to cross off negative 9. And our final answer is x equals 3. So I'm going to make a note so that we remember we can't take log of a negative number so only x equals 3 is our answer. And what ends up happening, this is called an extraneous solution. You won't need to remember that for pre-calc, but you might see that in future math classes if you go to calculus. So it's an extraneous solution, and the only answer I want is x equals 3. For D, we're not going to go through this one, but the one we just did will help, because since we have 2 logs on the left, you do first want to condense it into 1, and then you can go ahead and continue. I hope that helps.